Today we have this Cern Atlas virtual basics. We're able to set it up, and I'm so happy to have you here. First of all, I'd like to introduce our physics faculty. They have worked with Cern for a number of years. Especially we have Dr. Joe Haley. He just get back to the U.S. from Cern, so I would like to invite him to come up here and tell us a little bit about the time that he was over there at CERN.
So, hi everyone. Thank you very much. Yeah, so we have, I should mention, 3 professors at OSU working on the Atlas experiment at CERN. Dr. Rizatanova in the back and Dr. Konov sitting here, as well as an engineer who works for us who was a graduate of OSU and then came and worked in our group on the engineering projects. And you'll hear a little bit more about that in a minute, and that's Stephen Welch here. So yeah, we work on the Atlas experiment at CERN. I have a couple of quick questions just to get a feel for the audience. Who has heard of the Higgs Boson? Okay, so about 50-50. Okay, who knows what a particle collider is? Okay, 60%. Okay. So let me first maybe just set a general kind of make sure everyone has the general idea before I go into more details. And you'll hear more about this in the virtual visit. The virtual visit will basically be talking to people at CERN, one host at CERN who will be in the control room for the Atlas experiment, and they'll probably be saying some of the same things I'll be saying now, but just to get everyone started off. So our goal from a physics point of view is just to understand the most fundamental laws of physics. You could say that the ultimate goal is to find one equation that you could write on a t-shirt, and with that equation, in principle, you could describe anything that happens, any physical process in the universe. We haven't got there, but right now what we have is one equation that fits on a t-shirt that describes almost everything that we've measured, but there are some things that don't quite fit, and our goal is to kind of explore those things that we don't quite understand so we can understand them better. The way we do that is by colliding particles together at really, really, really high energies, as high of energies as we can achieve. The reason that's important is, so I'm sure everyone has heard E equals mc squared. So energy and mass can be converted into each other. And in fact, mass is just a type of energy, it turns out. So something with mass has energy just because it exists. If you have a particle with more mass, just sitting there, it has more energy. And the theories predict new particles, the theories that could be the final theory that you could write on a t-shirt, they all predict new particles, and those new particles have higher masses than we've seen before, or else you would have seen them. So they necessarily have higher masses than the ordinary particles that we know about, and so we want to create those particles. If we can create one, then we know that theory X is right and theory Y is wrong, or whatnot. And so to create a particle with a lot of mass, we need a lot of energy. So the purpose of the collider is to collide particles, in this case protons, pretty well-known particles. You take a hydrogen atom, take the electron off, and you have a proton. We accelerate those, collide those together with a lot of energy, and sometimes, every once in a while, we'll create a new particle like a Higgs boson that doesn't exist normally because it has a really, really high mass. So for those who don't know, the Higgs boson was discovered in 2012. It was hypothesized in 1964. So it took 48 years for it to be discovered. It was the most difficult particle that we've ever discovered, I think. We had known about it for longer than... There are other particles that had been predicted and discovered in the meantime. And the Higgs boson was so important because it was the only reasonable way that the theorists could explain why other fundamental particles had mass. It turns out that the theory that we have now, if there isn't a Higgs boson, then it's mathematically inconsistent for an electron to have mass, but we know an electron has mass. It's mathematically inconsistent for quarks, which are the particles that make up protons, to have mass. And so until we found the Higgs boson, we couldn't really explain, we didn't really know why an electron had mass, because if you worked out the equations and the electron had mass, and you didn't have a Higgs boson, then I think someone's trying to connect.
Oh.
Yes.
Oh.
So this is the Atlas control room.
So this is Cern.
We're connected in right now.
Yeah, I think they're testing.
Good afternoon.
I put on camera privacy. And
So, but our microphone is muted. But so they're ready for us when we start. So we discovered the Higgs boson, and our goal now is to discover new things. The Higgs boson is 126 times more massive than a proton, and other particles will be more massive than that. So that's kind of our goal. And so yeah, I spent a year living at Cern, doing research there every day. Before I was hired here at OSU a year and a half ago, so I'm the newest faculty. Dr. Rizzetanova started the experimental group at OSU 9 years ago, I think, and Dr. Khanov joined a couple years after that. So I'm the newest member, and we still now do our research there, but since we are generally located in Stillwater because we're teaching and things, then our research is done through this video conferencing. Well, our research is done mostly on computers, and then on a day-to-day basis we have video conferences with people at Cern. And in fact, people from around the world, every continent except for Antarctica has people working at Cern. It has, on the Atlas experiment, which is the specific experiment that we work on, there are over 3,000 scientists working. That's including basically faculty, postdocs, and graduate students. And then in addition, there are numerous, hundreds of engineers, or even hundreds of engineers like Stephen working to build this thing. So maybe now I'll hand the floor, or I guess I could take any questions specifically right now, so you guys have a chance to. I've flooded you with a lot of information. Maybe now I'll hand the floor over to. Should we go to this video of Stephen?
Yes.
Yeah. So now we have a video that Stephen is in. It's an interview talking about the construction of one of the parts of the detector, which was a huge upgrade project that was basically built over the last couple of years and installed in the Atlas detector over the last few months, and we will be, well, they're testing it now in the control room, in fact, now that it's installed. So do you want to make any more introduction to the video?
I actually don't remember the video, so let's just go ahead.
Okay, fair enough.
Okay, hello everybody.
Hello.
First of all, I would like to apologize because Steve can't host the visit. He didn't arrive yet and he asked me to replace him, if it's okay for you.
It's fine, yeah. It's fine.
Yeah.
Please go ahead.
Okay, so I would like to introduce myself. My name is Mohammed Al-Haroub. I am from Palestine, working at the University of Oklahoma, not far away from you. I finished my PhD in particle physics from Germany, from Bonn, and I'm now working again at the University of Oklahoma, but based at Cern. So I have to take care of the students, make shifts in this control room, and do other detector development. So the main thing I do at Atlas is the physics analysis. So I'm a pure physicist, not an engineer or doing detector or accelerator physics. I worked on top quark production through flavor changing neutral current, which is a very rare signal, and it's extremely suppressed in standard model, but many physics predicted it. And later I worked on top quark production associated to the Higgs boson And finally, when I joined the University of Oklahoma, I started to work on topic work in association to the Higgs Boson. In the meantime, of course, or as a second project, I work on Atlas cooling. We are developing or measuring the new coolant liquids for Atlas in our detector. And of course, because I'm based at Cern, I had to contribute to the Atlas operation. So we had to make many shifts. Atlas is a huge detector. It's 50 meters long by 27 meters in diameter, and it weighs 7,000 tons. From many sub-detectors, sometimes we call it onion structure. Let's start from the innermost part to the outermost part. So closest to the interaction point, we have the pixel detector made from silicon pixels, 400 by 50 microns. It's like any digital camera, like your digital camera, like your mobile, but it's much more precise because it's made from 92 megapixels. My camera, for example, is made from 20 megapixels. In addition, this one can take 10 or 20 or 100 frames per second. Atlas can take 40 million frames per second and 3D picture. Now, pixel detector helps us to identify the location of the protein which we need in order to start the tracks and to suppress the background. And also it helps us to measure the tracks and the trajectories of the charged particles. Because when we measure the trajectories of the charged particles, we can measure the curvature of radius of curvature, which helps us to identify the electric charge and the momentum of the particles. Now the pixel detector is a part of the tracking system. So we have other parts like the semiconductor tracker, which is again made from silicon, but big strips, not small pixels, 5 centimeters by 50 microns. And we have the transition radiation tracker, which simply stores filled with xenon gas. So when the charged particles like muons or electrons hit the gas, they will ionize it. And we have electric pulse, and if we know the position of the straw, we can estimate the trajectory of the particle. In addition to the momentum and the electric charge, we need to measure energy, and we use calorimeters for that. Calorimeters, we have two calorimeters. The first one is called Electromagnetic Calorimeter, which helps us to measure the energy of electrons and photons. And when I say electrons, I mean also the antimatter of electrons, the positrons. Also, we have the hadronic calorimeter, which helps us to measure the energies of hadrons. Those are composite particles made from quarks and gluons. For example, protons and neutrons are hadrons because they are made from 3 quarks and 8 gluons. Now, by measuring the energy and using calorimeters and momentum using tracking system, we can calculate the mass of the particle, and of course later we can identify it. Also, we have muon spectrometers. They are the biggest Atlas sub-detectors, and they are the latest part of the detector. They are like the tracking system, but they help us only to measure the trajectories of muon particles, because other particles are stopped by the calorimeter. In addition to the sub-detectors, we have also two magnetic systems. The first one is called the magnetic solenoid, which envelopes the tracking system. We need the magnet to force charged particles to change their trajectories to be able to calculate their momentum and their electric charges. And the second one is called the toroid magnet, which helps us to measure the momentum of muon particles. Now, given that we have a huge experiment, a huge detector, very sensitive, very expensive, it cost us more than $300 million to build it and more than 20 years to design and build the experiments, we have to take care about the safety. Safety, because we don't want to destroy it, and also we would want the experiment to run with the maximum possible efficiency. Because this increases the chance of discovering new particles. When we run the detector, we need every module, every sub-detector to be working as predicted. And also, sometimes we have problems and we can't solve them. I mean, if there is a dead module, we can't go to the detector and replace it immediately. We need 3 years until the next shutdown. But what we do, we record the problem into the database. So when physicists analyze the data, they should consider the problem into account. Else they end with false discoveries, because the way how we make a discovery is by looking at the prediction and at the observation. And if our prediction is wrong because we did not consider the hardware failure, then we have wrong conclusion. So we have this control room. Nowadays it's full because soon, in 2 weeks, we will start the LHC and we will have collisions and we will record data. So we started Atlas. Now most of the Atlas sub-detectors are on. They are coiled, the magnets are on, and we need to monitor every sub-detector from now, because we would like to discover the problems and solve them before we start collecting data. Of course, each shifter will monitor one sub-detector. I mean, each one will be trained to monitor one sub-detector. No one can monitor all sub-detectors. For example, the first disks, maybe I can show you. So each shifter will monitor one sub-detector. Some of them will monitor the innermost detector, the pixel, the semiconductor tracker, the TRT, the transition radiation tracker. Other shifters will monitor the calorimeters, magnets, data quality, trigger system, immune spectrometers, and of course each Atlas member should come here and contribute at least 20 days per year to be qualified as an Atlas author. This is one of the requirements. I mean, it's not enough to come to the data and analyze it and claim discoveries. I mean, you have to contribute to the operation, you have to write software, you have to validate it, you have to monitor the detector. Of course, we monitor Atlas 24 hours a day, 7 days a week. No matter if we have data or not, of course, during the running time. Okay, this is an introduction to the Atlas, and I hope you have more questions about physics or hardware. I made it so fast, and I'm sorry because I was not prepared to be the host.
So, Muhammad, maybe you can say how many shifters usually are sitting during the data taking? How many? 30 people? 40 people?
Again?
How many people are sitting during the data taking shift?
How big the data is, you mean?
No, how many people are sitting in the control room?
Yes, I mean, nowadays when we have data, I mean, we need 12 shifters plus 8 to 10 expert shifters. Right now, the control room has more than 12 because many expert shifters are here training or debugging the system. But in case we have a stable system and no problems, just 12 people maximum.
Okay.
So one, for example, for the innermost detector, so the tracking system. So one will monitor the pixel, the semiconductor tracker, and the transition radiation tracker together. One will monitor the calorimeters, another for immune system, and also we have a shift leader and run control role. More questions?
Yes. What kind of safety measure you have in case of meltdown or some sort of disaster.
So just to repeat, the question was, what sort of safety measures do you have in case of a disaster?
Oh, do you mean safety measures for human beings or for I mean, we don't expect disasters because the detector is under the ground 100 meters and nothing can go wrong to us. I mean, when we collide the protons, okay, we have a little bit of radiation, but we are far away, and the detector and the detection mechanism will stop all these radiation. For the detector safety, yes, we have thousands of safety measures. We need to monitor the temperature. We need to monitor the humidity. We need to monitor the electrical current, high voltage, low voltage, because we have really sensitive material, and we have to take care, because if one system fails, of course, it will reduce the performance and the efficiency of the detector, which is bad. But if you care about us, don't worry. First of all, nobody is allowed to go down to the detector, and plus we are far away from that. And the amount of radiation we have is really much less than the radiation we receive on the surface from the cosmic rays. Of course, if you stay next to the detector, there is a risk that you will be harmed in case of, let's say, cryogenic leaks. We have liquid nitrogen, which is extremely cold. We have liquid nitrogen and other things. We don't have the problems, but in case you have a problem and you are there, you will feel really cold. But hopefully we don't have these problems.
Because that's the only problem, yeah? Go through reports. Yeah, just in
I
case.
think I'll just add, in addition to that, when, for example, there was a shutdown to put things into the detector, so there were people working on it. Also, there'll be periods where if something goes wrong, if some part of the detector breaks, and we need to go in and fix it during like a short, maybe like a 1 day, they'll turn things off and allow us to go in. And in that case, the people who go in have to be specially trained in radiation. They go in with radiation detectors to verify that the levels aren't very high. And then there are many safety measures in place where each person has a key. It's kind of like you think of like a sci-fi movie. Each person has a key, and someone has to insert a key on one side of the door and turn it, and then go through the door, and the other person on the other side has to insert a key and turn it, and go through in pairs, so that there are many safety measures, so that it's never possible for a single person to be in there alone, and anyone in there has to have a key, and the detector can't be turned on until all the keys are returned to a base station and things like that. So yeah, Cern is very, very careful with safety, because it would be horrible if anything went wrong.
So this location right now, are we on the surface right now?
This is on the surface, yeah.
Okay, how far below?
100 meters below
Okay.
is where the detector is.
How long are they shut down every year? He said you're in a shutdown phase now. Is it just for repairs?
Can you hear us better
So
now?
there are two different types of shutdowns.
I need the headphones because lots of noise around.
And can you hear us?
Can you hear us?
There are short maintenance shutdowns.
Yes, I hear you.
So maybe we can, we'll ask, so try to ask your question one more time, maybe. And
Sure.
you can-
Wait till he gets head on.
But please slowly, so I can hear you better.
How much time are you shut down each year for repairs and so on?
So you ask about the shutdown, the long one or short one?
Both.
I think just in general, usually how long is the detector in the collider shut down?
I mean, every 4, 5, 6 weeks we have short shutdown, a few days for maintenance. Not on the detector, but mostly on the readout system. And some upgrades here and there. Every few months, 1 or 2 weeks for maintenance during the data taking. But every 3 years we have long shutdown for major upgrade. For example, we run Atlas 2010, 11, 12, and the first month in 2013, but then we have 2 years shutdown. We opened the detector, we replaced we took the fixed detector, we added the 4th layer, we Then we replaced all the modules, we improved the detector and of course the accelerator. So we have shutdowns 1 day, 2 days, every 4 weeks let's say. Then we have every few months 2 weeks. Then every 3 years we have 1 or 2 years for the major upgrade. This is the usual program. Unless we have serious problem, which never happened and hopefully it will never happen.
You could ask him, in between the shutdowns, the collider apparatus is fully powered and in a state where different research organizations can use it for research purposes in between?
So the question was, so during the shutdown, or in between?
In between the shutdown.
Okay, so well,
when the system's operational.
When the system's operational, who is allowed to use the collider, or how does an organization get access to using the Large Hadron Collider?
And is the collider fully operational during those times?
And is the collider fully operational during the running times?
So if we have a shutdown, it's coordinated with other experiments and the Large Hadron Collider. Atlas does not have its own shutdown. So they coordinated with CMS, the other big experiments at LHC, ALICE and LHCb. So in the same time, of course, to minimize the shutdowns and to increase the efficiency. And then we have shutdown. Each experiment works on it, or each collaboration works in its experiment, and at the same time, of course, they work on the LHC. In the meantime, okay, the engineers, technicians work on the detector, and physicists continue to calibrate the data collected during the operation, and continue, of course, the analysis and making the physics measurements and their publications. During the data taking, the LHC is running Atlas and other experiments collecting data, and as soon as they collect the data, they store it, they calibrate it, and then of course they make it available for physicists. And then once the data is available, physicists look at the data. Of course, everyone is interested in one physics channel. For example, I am interested in the topic quark, others interested in the Higgs Boson, and everyone is interested in exotic models or supersymmetric theory. And what's a signal for me is a background for others. So there is a little time delay between collecting data, calibration, and analysis. And of course, data publication, which can take 1 or more years until the physics analysis is mature enough and convincing.
So the short answer is yes. And also, one point is that, as Muhammad was saying, there are 4 main experiments and also a couple of smaller experiments that are basically, they all work together with the collider.
So Atlas is a client research project.
Yeah, it's a
within the scope of the entire Cern capability.
Yeah.
Actually, there are other research going on, but what they do, they have a magnetic system that can, pick up some light from the beam and direct to another research project. For instance, when you have so a lot of this work that has been incorporated into the Atlas technology has been tested on the beam test, so-called beam test. So what you do, you don't have a full power beam, but you do have smaller energy beam, and you test every single component before you will put it into the Atlas detector or any signal detector. So basically, what people do, so the LHC, we call it LHC, Large Hadron Collider, but in fact, it's a huge accelerating problem. It starts with very small energy and it increases gradually. So it's a set of accelerators actually that we call Large Hadron Collider. And for some of those smaller accelerators, you can derive the beam and use for medical purposes, use for technology purposes, use for NASA studies, and for any other research program. So CERN is based, of course, the main goal is just to study fundamental questions of the universe. But in addition, people understand that these fundamental questions of the universe can be answered in another way, that is not the space program. So other, and have a lot of applications, as Joe says, like medical application and engineering application. So all this stuff is just, taken into account. And not only research, but arts. Cern has very, very interesting art program. They incorporate, they invite artists
I guess
every
like science
year.
inspired art.
Yeah.
It could be said that the Cern facility is a scale of Fermilab.
Yep.
Yes.
It's
Much larger, I would say.
Fermilab is the U.S. Center for High Energy Physics.
In
Cern is the
outside
European.
Scotland.
And Cern is the European equivalent. And since Europe is made up of many countries, they have a little bit more money than they can clear. I'm sorry?
The Triumph Center in Canada,
Yeah, more questions, do you have
Do we have more questions?
I'm not familiar, but I would probably. In fact, Fermilab has many scientists working,
Go ahead.
and Fermilab works on the experiments at Cern. So
There is one more question.
Joe, can you ask him what are the exciting things are we expecting from Run 2?
So the question is, what kind of exciting things can we expect from Run 2?
Oh, in principle, we don't know. Because if we know what we are going to discover, there is no need to make the experiment. We are looking for surprises. But we hope there are many, many things to discover, because we are going to double the energy, which means we are going at least to double the production rate for many particles. And also we have the chance to discover particles with heavy mass, because every time you increase the energy at the center of the collision, you scan the higher mass range. It could be SUSY, for example, supersymmetric particles. It could be exotic models.
Extra dimensions.
It could be something we never predicted. So this is the fun about particle physics. Sometimes you look for something, you don't discover it, then you come back to your colleagues, the theoreticians, and tell them their theories are wrong. And sometimes you look at the data and you find a nice peak and nice discovery. Who knows? But again, there are many scenarios. It could be supersymmetric, it could be exotic models, it could be.
But maybe we can say that what is the physics program at RUN in the RUN 2B? So the main physics focus will be on search for dark matter candidates, search for new particles that don't fit into the standard model, classic models, new forces, and new types of interactions, right? So that's basically what we are looking for. And of course, to verify to continue to improve accuracy of the measurements of the environment. So for instance, we would like to improve the mass measurement for the Higgs boson, for the standard Higgs boson. We would like to improve the mass measurements of the top and other things which really significantly affect the predictions of what might happen in the future. Yeah.
Any more questions?
I know that there are 4 detectors around the ring, so is this
And so the question is just to get a better idea about the different detectors around the ring. So maybe you can say a little bit about Atlas versus CMS versus LHCb and how they fit into the picture of Cern and the Large Hadron Collider.
So when we have the beam at the LHC, of course, and if you have one detector, then you will be limited and biased by the choice of the technology, by one collaboration, which is bad. For example, if there is a false discovery or there is a discovery, we don't know whether it's true or it's wrong unless there is another collaboration with independent detector, different choice of technology, statistically independent data, different algorithms, discover or rule out the theory independently. So we need another experiment, and of course it's CMS. Now if Atlas makes a discovery and CMS does not find it, either of us have a problem, and we have to work hard to see who has the problem, Atlas or CMS. But if we both make the discovery independently, as we did when we discovered the Higgs boson, then we increase our confidence in the discovery, because it can't be the same problem, because our machine is big and light, their machine is small and dense. We are different physicists than them, we use different algorithms, so it has to be a real discovery. Now, ALICE and LHCb are two special experiments. ALICE was designed and built for lead-ion collisions. 1 month per year we accelerate lead ions, not protons, and those are really heavy nuclei. They are made from many protons and the neutrons, and when we collide the two lead ions, we provide enough quarks and gluons at the center of the collision. So we can create a quark-gluon plasma. A plasma, or let's say fireball, contains quarks and free gluons. And this plasma only existed after the Big Bang, within 1 millionth of a second after the Big Bang. So we are reproducing the conditions existed after the Big Bang. And if we study the dynamics of this plasma and how it expands and cools down, somehow we can understand how the universe evolved within the first 1 millionth of a second of the Big Bang. Now, the fourth experiment is called Large Electron Collider Beauty Experiment. Beauty because we are looking at the hadrons, which are made from beauty quarks and other light quarks. Now, they are interesting because they are unstable particles. They decay very fast after we produce them, and when they decay by a weak interaction. We have 4 mechanisms in nature: gravity, strong force, weak interaction, and electromagnetism. 3 of them we don't know so much about the gravity, but we know about the strong interaction and electromagnetism. And those say that every time you produce matter, you produce equal amount of matter, and when you put them together, you annihilate both, which means that we have perfect symmetry between matter and antimatter. The third one, the weak interaction, tells us there is a small difference between matter and antimatter. So they are not identical. And we would like to explore this difference more and more, because this might help us to understand why the antimatter disappeared in the universe. So this experiment again was built and designed and built to detect the hadrons, to study their decay modes with high accuracy. So these are the 4 experiments, and these are the differences between them.
And just to give an overview, or also to give a recap, so there are 4 main experiments, and each one then has a controller like this. So Atlas is one of...
Is it okay?
Yeah.
Yes.
Yeah, I'm just giving you a quick recap on what you said. So Atlas is one of the 4. It has this control room. So the CMS experiment is like Atlas, and it's on the opposite side of the ring. It has a similar control room.
Hello?
Hello?
We can hear you.
And then the
Can you hear us?
other 2 experiments are other places, and they're more dedicated. So each of the 4 have a similar setup to this, and then
I can't hear you.
The collider is just running through all 4 of them. So this kind of goes back to your question. When the collider is on, it's colliding at all of the points that are looking for the things, except that, as you're saying, the ALICE detector is specifically looking at the collisions when we have lead ions. And so instead of colliding protons, they take a lead atom, they remove an electron and make an ion, and then they accelerate that. And so ALICE is only turned on when they're doing those collisions 1 month out of the year. And the other ones are looking at all of the other. The ATLAS detector was designed to look at the proton-proton collisions, but we also use it to look at the lead ion collisions just because we can. I mean, it works for that too. And so there are two people who work for Atlas who are interested in those ones specifically. And they're sitting, like he said, trying to understand what happened in the fractions of a second after the Big Bang, not looking for new particles, but understanding the particles we already know about and how they interact in these really, really, really high energy situations. And then just a bit of terminology. So Cern is the laboratory. Lots of things go on inside there. And the Large Hadron Collider is just the main machine that they have, but then there are smaller machines that do other things. And then Atlas and CMS and ALICE and LHCb are just 4 of the experiments that use the Large Hadron Collider. So there's like a hierarchy. At Cern, people work at Cern to just do medical research. Completely independent of the Large Hadron Collider, and things like that.
There are 4 collision sites.
But in fact, there are 8 possible places, but we don't use all of them. If we had infinite amount of money, we would build 8 detectors.
It just means that OHC is on. But it won't be off forever. It will come back on.
Maybe should we?
I'm pretty sure it's this month.
Maybe we can, is there any more questions specifically for the virtual visit, and then we can cancel that, and then maybe have 15 minutes of just Q&A here, because it's a little bit easier. So are there any more questions specifically for Mohammed? Okay, I think that's it. So thank you very much, Mohammed. Too bad about the technical difficulties, but thank you very much. It was great, and I'll see you probably this
By the
month.
way, this visit is broadcasted and it will and it's recorded. So I think within a week from now you can watch it again. Of course, we need to make montage and cut it and it is much better.
Thank you.
Thank you, Wafan.
Thank you.